So we initiated discussion on view factors in the last lecture. So we're going to continue forward with that and look at other methods which are available to evaluate view factors. So what we are going to see now is, in today's lecture, is called the inside sphere method. So note that if you want to find the view factor for any system, you can always integrate the expressions that we had. So we looked at the summation rule and the reciprocity relationship, which will help you to calculate the view factors quickly. We're going to look at another method called the inside sphere method, and this is a very handy method to calculate view factors for various kinds of three-dimensional geometry. Okay. So suppose so I have a sphere, okay, and let's say I have a surface A2 and I have, let's say, another surface A1. Okay, I have two surfaces and I need to find F12, which is the view factor for emission which is emitted by surface A1 and how is that received by surface A2. Okay, so we need to find the view factor or the geometric factor. Alright, so let's say that this is the center of the sphere, and if I assume a differential element here, so this is dA2 and this differential element is dA1. Okay. So if the sphere is, the radius of the sphere is r, then obviously the center distance from the center to any location in the sphere is r, and if the linear distance between the two is s. Okay, so that's the linear distance between the two surfaces or two differential elements. Okay, so the objective is to find F12, and the formula for F12, the integral is 1 by A1 integral A1 integral over A2 cos theta 1 cos theta 2. So if the angle here is theta 1 and theta 2 and the angle here is theta 1, okay, so then I'll have F12 is 1 by A1 integral A over A1 integral over A2 cos theta 1 by cos theta 2 pi s square into dA1 dA2. Okay, so that's the view factor. What is cos theta 1? Cos theta 1 is, let's say I drop a perpendicular line, so this distance is s by 2, so cos theta is s by 2r, and that's also equal to cos theta 2, okay, because it's a isosceles triangle, and so the angles are same, and that's equal to s by 2r. So now if I plug this in, A2 s square by 4r square into 1 by pi s square dA1 dA2. Okay, so we cancel out s2, so that will be 1 by 4 pi r square. So note that r square, the radius of the sphere, is independent of what is the area of A1 and A2, and it is independent of the location of the surface areas. So that will be, and so that will be 1 by A1 integral A2 dA1 dA2. Okay, and that's nothing but A2 by 4 pi r square. What is 4 pi r square? It's the area of the whole sphere, right? So that's nothing but A2 by the surface area of the sphere. So that's an interesting formula. So note that the view factor F12 is now completely independent of where these two are located. It's independent of where these two are located along the surface, and not just that, it depends only on the receiving surface area. So it's independent of the size of the surface area, which is size of the surface which is emitting, and it depends only on the surface area of the receiving surface. So this is a really useful and very, very important formula, and in fact we will see several examples mostly in the next lecture or the one after. When we look at several different problems, we will see that this formula actually comes in very handy to calculate view factors for various three-dimensional geometries. Particularly because you don't have to calculate or you don't have to construct the three-dimensional geometry anymore. If you are able to use this formula straight, you don't have to construct the three-dimensional geometry and do the integration. So it becomes very handy if you really understand what this formula means and how to use this. That's very important. How to use this formula for solving or finding view factors for various kinds of problems that you will be looking at in the future. All it assumes is that it's a diffuse emission, and what you account for is radiosity. So that accounts for both emission and reflection. Everything is accounted. The only assumption which is important here is that we assume that the emission is diffuse. Now if it's not diffuse, then you will have to integrate over the whole angle, all the angles in all the directions. So if the emission plus reflection, the radiosity is a diffuse radiosity, then this is a golden formula that will be very, very handy to solve different kinds of problems. So it sounds very counterintuitive, but this is one place where actually intuition doesn't work. So if you actually plug in all the formula, it doesn't matter where you place the surface area. It really doesn't matter. So that's a very, very startling result that you will see. It's completely counterintuitive, but it's very, very useful. You can actually construct a whole three-dimensional geometry and integrate, you will get exactly the same result. So we haven't done any magic here. It just comes out from the formula which we had derived rigorously in the last lecture, and we've just applied the formula with the normal angles that we already know. So all that matters is that the geometric factor, if the areas are placed inside the periphery of the sphere, this is very important. If the surfaces are placed in the periphery of the sphere or the surface of the sphere, irrespective of where the emitting surface is located, the view factor only depends upon the receiving surface area and the total sphere. Okay? So that's a very, very useful formula. Any questions on this? It is counterintuitive, and the reason why it is counterintuitive is that you would always think that, if I have to place the surface here, then how come that it depends only on the surface area of the receiving surface? But note that the area of the sphere is still here. So it is accounted in some sense, the area of the emitting surface is in some sense accounted in the total area of the sphere, but it just turns out that it's irrelevant. It's irrelevant what is the size of the area, and where it is located is completely irrelevant. And similarly, where the second surface is located is also completely irrelevant when you want to calculate the view factor. It just turns out that it's completely irrelevant. It is counterintuitive, and we have not done any magic here. It's completely rigorous. Okay? Alright, so this is a very, very useful formula that you must all remember. So recall that when we initiated discussion on view factor in the last lecture, the objective was to characterize radiation exchange between surfaces. So once we know how to calculate view factor, we can now attempt to find out what is the net radiation exchange between different surfaces. So that's what we are going to do now. So supposing we take real surface, So we know that real surfaces absorb and emit at all wavelengths, all lambda and all theta and phi. Okay. But with Blackbody, we have a special property. Blackbody has a special property. What is that property? What's that property? What's the special property of Blackbody? It absorbs all incident radiation, right? So Blackbody is a diffuse emitter and absorbs all incident radiation. All incident radiation, which means that reflection is 0, right? So this simply means that reflectivity is 0 for a Blackbody. Okay. So suppose I have two Blackbodies. Okay. Okay, I call it I and J, and let's say that the temperatures are Ti and Tj, and the surface areas are Ai and Aj. Okay. So now the emission is going to occur at all locations in all directions. Because it is diffuse, it's going to be equal in all directions, right? It's a diffuse emitter. So now the question is, what is the net rate of heat exchange between these two surfaces? That's what we want to find. So what is the net radiation exchange between I and J? That's what we want to find. Okay. So Q net will be, so all of you must have heard that sigma Ti power 4 minus Tj power 4 will tell you the net radiation exchange. But what is missing? That's not the complete story. What's the key assumption that you make? That's okay, forget all the conduction properties. Let's say there is only radiation mode of heat exchange. What's the key assumption that you make when you use that formula? That's fine, it's a Blackbody, so it has to be a diffuse emitter. Yes? E equal to? It's a Blackbody, so it's a Blackbody radiation. View factor, you see? So that's the first and primary assumption that you make. You assume that view factor is 1. So most of the radiation calculations that you would have done so far, you assume that the view factor, the geometric factor, they are all geometrically aligned, and that the geometric factor does not contribute anything to the radiation exchange. So remember that in last lecture we said that one of the crucial properties that you need to find out if you want to calculate radiation exchange is the view factor. You cannot assume that view factor is 1 between any two surfaces. This is the fundamental underlying assumption that went into all the calculations you have done so far. Okay. So the first observation is that Fij is not equal to 1. Okay. So therefore, the net radiation is simply the difference between what is emitted by I and received by J minus what is emitted by J and received by I. Okay. So this Q is given by Ai, Ji. So that's the net radiation, rate of radiation emitted by surface I multiplied by the corresponding view factor, right? So that's what tells you what is that fraction which is received by the surface J. Okay. Minus Qji is given by Aj, Jj, F, Ji. Okay. So this Aj into Jj, that is the rate at which the radiation is emitted by surface J, and what fraction of that is intercepted by surface I is given by product of that with the view factor. Okay. So from reciprocity relationship, we know that Ai Fij and Aj Fji are related, right? So that will be Ai Fij Ji minus Ai Fij into Jj. Okay. So that's equal to Ai Fij into Ji minus Jj. What is Ji for Blackbody? So keep in mind that the properties of Blackbody are such that it's a diffuse emitter and it absorbs everything, which means reflection is 0, right? So Ji is just the emission from the Blackbody, and that's given by Stephen-Boltzmann law, right? So that's where the sigma T power 4 comes in. So that's equal to Ai Fij Ebi minus Ebj. So that's the Blackbody radiation, and so that's equal to Ai Fij sigma Ti minus Tj to the power of 4. Okay, because there is no reflection, so note that this is because reflectivity is 0. Okay, that's why Ji is equal to Ebi. There is no reflection from any surface, it's all the emission that from that surface. So the net radiation exchange between the surface is this quantity. Now why is this important? Why is this important? Why do we need to know what is the net radiation exchange? Supposing if I want to maintain the temperatures, okay, so let me put it in a different way. Supposing if I want to maintain the temperatures of these two surfaces, this is the amount of heat that either I have to provide to a body or remove depending upon the temperatures. So Q net can be positive or negative depending upon what is Qij and Qji. We don't know that. We have to put the numbers and find out whether Q net is positive or negative. So for a given body, if Q net is positive, right, which means that there is a net radiation that it is actually taking because of radiation exchange. Therefore, there has to be a heat sink inside that surface in order to maintain a constant temperature. If you want to maintain an isothermal temperature, then that's the amount of heat that has to be removed from that system if Q net is positive. Now supposing if it is negative, then that's the amount of heat that you have to supply. So this is a very, very important property. Remember that in conduction, we always said you always have to find out what is the net amount of heat that you have to supply or remove from the system. So that's the whole purpose of calculating the radiation exchange. Of course, Blackbody is an idealization. We are going to see how to do this for a gray surface in a short while, which is a real system. Okay, so Blackbody just gives you an advantage to an idealized system to understand how the system is behaving, because all the properties of all the radiation properties are scaled with respect to that of the corresponding Blackbody. Okay. Alright, supposing I have n surfaces like this. Suppose I have n Blackbody exchanging radiation. Suppose I have n Blackbodies, then what will be the net radiation exchange? What will be the net radiation exchange? It will be sum over all I, right? So it will be sum Ai Fij, so it will be sigma Ti to the power of 4 minus Tj to the power of 4. So this is the net radiation exchange of the ith surface, and it is summed over 1 to all n. Okay. So this is without loss of generality, we have written this formula. You don't have to assume that there is no radiation exchange between itself. So that's also accounted for here, because J equal to I would be Fii. So that accounts for radiation exchange with itself. So if it's a convex surface, then FII will be 0. If it is a concave surface, it's not 0. So this is a general representation of the net radiation exchange with n surfaces.